Okay, work part 3. Let's talk about working with springs. Now, Hooke's law, as you probably know, is uh, minus k times d, which means if you have a spring and if you just have it sitting at rest, nothing pushing on it or pulling on it, it has some kind of length. And if you compress it, the force of the spring will be opposite the direction you've moved it. That's why the negative times a spring constant, how stiff, a measure of how stiff the spring is, times the distance. And it's a linear relationship, a constant times the change in the distance. If you stretch it, the force will be of the spring will be opposite direction, so it's still negative times the spring constant times the distance. This makes it, if you were to graph it, if you make it longer, it takes more and more force linearly. If you make it shorter, it takes more and more force. It's kind of an absolute value type function. And these work problems with springs, since it is linear, you can take the average force, the force at the beginning, the force at the end, take the average times the distance, you change it, and you get the work. You don't have to use calculus. But let's go ahead and do it with calculus. So let's take a spring, and let's say its constant of work is something like it takes 3 pounds to stretch it. This is a tough spring to stretch it, a tenth of a foot. Tenth of a foot, a little bit more than an inch. So whatever the spring is, I try to do that. It takes 3 pounds of force. It takes another 3 pounds to do the next inch, 6 pounds to do the next. So it's a linear relationship. So you don't really need to worry too much about the negative. You just need to know what's going on here. So the force at the beginning, when you first start moving it, it's going to be 3 pounds per tenth of a foot. So that's 30 pounds per foot, assuming you have a big spring, it can go a foot. Often these are not in pounds and feet, but something smaller units because you're dealing with a smaller spring. But let's say we got a huge piece of machinery with a large spring on it. Times the distance it's moved is gives you the force. So if it's compressed a distance of, let's say 2/10 of a foot, you take that times there, and that's how much force it is to get it to that position. So the work you put into this, which gets stored as potential energy, can get released when you let go. The work is neither positive nor negative to really worry about, so don't worry about that negative on it. And you're going to do something like this. You're going to say, well, it's force times distance is work. And the force is going to be 30 pounds per foot of movement times the distance that it's been moved. That's the force. And then you're going to move it a small distance. So this is all linear, so let's just make that an x direction. We'll move it a small distance. And then if you move it a very tiny distance, then the force changes because now the distance has changed. And so then the work becomes the new force times the distance. And so you just have to decide from where to where are you moving it. 30 pounds times whatever distance it starts, Whatever distance you move, you're at, wherever it's at, times the change of distance, and you're going to move it. Let's say you went from 1/10 of a foot to 2/10 of a foot. That would be the work in foot-pounds put into compressing the spring from 1/10 of a foot to 2/10 of a foot. And it would be the same for stretching it from 1/10 of a foot to 2/10 of a foot. Now, you could figure out the force at 1/10 of a foot, the force at 2/10 of a foot, average it because it's a linear relationship, and take it times the change in distance, which would be 1/10 of a foot, and you should get the same answer as this would give you. That's the work, part 3 on springs. Pretty simple, pretty straightforward.